Hi there. Next up in our journey through our periodic table is the lithium atom. So we just finished our discussion of hydrogen and helium, and now we're adding one more electron to the mix to get to the lithium atom. Okay, so here is our Hamiltonian for our lithium atom. So in this model, remember we have our nucleus, okay, of, we'll just say big mass M again. And then here we've got now three, just drop them evenly spaced, three electrons surrounding our nucleus. Okay, so again, very basic sketch here. So we have interactions between each electron and our nucleus. Okay, so we've got interactions going on here, and then we also have interactions between our three electrons. Okay, so we're going to have all of those interactions to describe with our Hamiltonian. Okay, so we have our kinetic energy terms, right, with our Laplacian operators there, corresponding to each of our electrons. Okay, and then we have the interaction between our nucleus and our electrons. That corresponds to these three terms here, right? So that would correspond to these three green interaction lines that we've drawn here. And then the last set of terms would be our interelectronic repulsion terms, those Coulombic electrostatic repulsive forces between our three electrons. Okay, so we've got the red lines indicating those interactions there. Okay, so a lot going on, right? We've already seen that for our even simpler case of helium. We're just adding that one extra electron to our system totally kind of prevents us from being able to solve our Schrodinger equation exactly. Things do not get any better by continuing to add more electrons. Okay, so we're in just the same boat that we've been in before, okay, where we have to use approximation methods to get any energies, energy approximations for this multi-electron system. Okay, so in terms of calculating the energy, you would still be looking at doing a variational or a perturbation theory calculation. So when we next look at the wave functions for our three electron system, we can start by just kind of filling them into our lowest energy orbitals, just like we've done for our two previous examples. So let's just place our electrons all in our 1s orbital. Okay, so we've got electron 1 in the 1s, electron 2 in the 1s, and electron 3 in the 1s, right? That seems like a reasonable kind of first guess for how things are going to be situated for our system. Okay, and you're probably screaming at me through the video, no, 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 that really feels wrong. And you would be right. Okay, so looking at what I have on this screen is probably making you itch in your skin a little bit. You're like, this does not look right, and that's because you've probably seen in other chemistry courses that idea of only being able to have 2 electrons per orbital, right? So that's our Pauli exclusion principle, right? So it is in fact still going to be an issue for us now. Okay, so we're going to take a close look at that idea of spin. Okay, so what's going to help us to solve this problem and figure out where our electrons go in our orbitals now that we have more than 2 of them, we're going to start diving into the idea of spin. So this is our 4th quantum number that we're going to tackle today. Okay, so again, summary, this is no bueno. Okay, so what is electron spin? Okay, so as I mentioned before, this is what's going to help us to explain why we can only put 2 electrons per orbital. which we've already, again, been familiar with in our general chemistry experiences. Okay, so normally our process for developing or deriving a new quantum number would be to solve the Schrodinger equation, and then it arises naturally out of the mathematics of doing so. Electron spin is a special quantum number in that there is no classical analogy for it. It does not arise naturally out of solving the Schrodinger equation, but it does, however, arise when we treat the motion of our electron relativistically, okay? But that is way beyond the scope of this course and generally beyond anything that chemists generally spend much time thinking too much about. Okay, so we'll leave that part to the physicists, okay, and we instead just kind of take electron spin as another postulate. So spin actually gained acceptance or acknowledgement via a number of experimental results that support the existence of spin, and those are listed here. So the Stern-Gerlach experiments, which is the splitting of a beam of silver atoms, any electron and nuclear magnetic resonance spectroscopy, so all the NMR work that you've been doing over the years is an experimental case for the existence of spin. Okay. Degeneracy of the excited states of atoms and molecules, something called the anomalous Zeeman effect. We'll talk about that a little bit more later. And all the fine structure splittings that we observe for atomic spectra. Again, something that we'll talk about shortly as well. Okay, so again, there's no classical analog. We're not going to follow our standard derivation of this quantum mechanical operator or quantum number like we've done for our previous examples. What we're going to do instead is just introduce spin by a series of postulates. And again, remember our postulates are just rules that just are really justified by the fact that they work. Okay, we just haven't encountered a situation yet where we've been able to kind of disprove that this works. Okay, so on to our postulates of electron spin. So our first postulate describes the operators for spin angular momentum. So this is another kind of clarification point here. When we talk about spin, it is essentially a version of angular momentum that we're working with. So everything that we look at, you're going to notice, is going to seem really analogous to what we've already talked about for our regular angular momentum, or what we could call our orbital angular momentum, L. Okay, so remember, orbital angular momentum was our L quantum number that we've already talked about. Okay, so we've got spin angular momentum operators that correspond to spin eigenvalues, okay, and our spin angular momentum operators also have directional components. So we will talk about our total spin angular momentum squared and the x, y, and z components of our spin angular momentum, just as we did for our orbital angular momentum L. Okay, so again, analogously to orbital angular momentum, we have eigenvalues that correspond to these operators that are given by our spin quantum number S. Okay, so S times S plus 1 times h bar squared for our total spin angular momentum squared, and m sub s h bar for s sub z. Okay, again, analogous to L times L plus 1 h bar squared for L squared, and m sub L h bar for L sub z. Okay, so just like before, just different numbers. Okay, so before we had options for L that were integers. Okay, so 0, 1, 2, 3, 4, all the way up to n minus 1. Okay, here our spin angular momentum quantum number is a little bit different, so it can take on integer as well as half integer values. So you are probably most familiar with the spin 1/2 quantum number. Okay, so that is the spin angular momentum quantum number for the electron. Okay, so turns out that is for any fermion or fermion, however you want to say it. Things like electrons. Okay, if you're talking about bosons, okay, again we're getting a little bit into more into physics than we really need to for our purposes, but those would have spin angular momentum quantum numbers of 1, and then they follow completely different rules than we have for the electrons. Okay, so we will focus on our electron rules, also known as fermions. Okay, and then we have our magnetic quantum number, spin magnetic quantum number that specifies the z component of the spin angular momentum. So this is essentially the quantum number that you're used to using when you're labeling the locations of your electrons. So whenever you've been asked what are the 4 quantum numbers associated with an electron, that last number, your m sub s, right? That's usually where you have your plus or minus 1/2 option. Okay, so that's, again, follows the same rules as our m sub l. That's going to range from minus s to s plus 1 all the way to s. Okay, so be careful that you don't go on autopilot and stick a 0 in there like we've been doing for our m sub l's, right? Because we are dealing with only integers for m sub l, you're always going to go through 0. That's not the case for your m sub s. Okay, so careful to not automatically include 0 here. Again, it's going to depend on what your spin quantum number is, but for electrons, you're going to range from minus 1/2 all the way up to plus 1/2. Okay, so when we take minus 1/2 plus 1, right, for our next term in the series, that brings us to plus 1/2. Okay, so we completely bypass the 0 there. Okay, so just don't go on autopilot on that one. Okay, and last but not least, our second postulate states that for a single electron, there are only 2 simultaneous eigenfunctions of the total spin angular momentum and the z component of the angular momentum, and they are called alpha and beta, with the eigenvalue equations as shown below. Okay, so again, remember these are the eigenfunctions. Okay, we just talked about the eigenvalues, so these are your measurable quantities. Okay, so these are the eigenfunctions that our operators are going to act on. So here are our eigenvalue equations. So this is the z component of our spin operator acting on the alpha eigenfunction, and we get out plus 1/2 h bar alpha. Okay, so remember we get our eigenvalue out front, and then we get our function spit back out at us. Okay, if we have that same operator acting on the beta function, the beta eigenfunction, that gives us the minus 1/2 eigenvalue. Okay, so minus 1/2 h bar eigenvalue, and then again we get our eigenfunction beta spit back out at us. Okay, same idea with the s squared. Okay, s squared acting on our alpha eigenfunction. Again, just plug in plus 1/2 for your spin angular momentum quantum number in the equation. Okay, here we're going to get, for both of these options, we'll get positive values out there. Okay. All right. So I think that is it for our postulates of electron spin. So this sets us up to be able to do a little bit of work with them.